We're now going to look at the algebra of matrices. In particular, the properties of matrix operations. The operations we've looked at so far have been addition, scalar multiplication, and matrix multiplication. So we're going to look first at the addition properties. First off, addition is commutative. What that means is, as long as the addition is defined, I can add two matrices as is, or I can switch the order around. Matrix addition is also associative, which means you can add, if you're adding three matrices together, you can add the first pair together and then add the third, or you can add the latter two to the first. So we can add the latter two first and then add the first one. So as far as pure addition goes, that's pretty much it. The addition follows the same properties as real numbers do. And you can verify each of these by actually adding the matrices component-wise. Each of the components are real numbers. Real numbers are commutative under addition and associative under addition, so that's why these properties follow. If we look at scalar multiplication, we also have that scalar multiplication is associative. What that means is you can multiply, if you're multiplying by two different scalars, you can either multiply the first scalar by your matrix and then multiply the second one. So we scale once, then we scale again. Or multiply those two scalars together, then take that final scalar and multiply that by your matrix. So this just says that the order works in the way that you think it should. Also for scalar multiplication, if we take the number 1 and multiply it by the matrix, 1 acts as a unit, which means when we multiply by it, it doesn't change the matrix. And you can verify this just by multiplying the number 1 times every component. 1 multiplying by 1 changes none of the components, so it doesn't change the matrix at all itself. Now if we mix these two together, addition and scaling, we have the distributive properties. There's actually two different versions of the distributive law. The first one is that if you take a scalar times a vector addition, that this will distribute through just like you think it should. That this gives you the scalar times the first matrix plus the scalar times the second matrix. We also have the second version of the distributive property, which is if we've got two different scalars, we can either add them together first and then distribute through to the A, or we can distribute the matrix A to each of those scalars. So we're doing two separate scalar multiplications and then adding the results together. So these are the sort of basic operations that involve just addition and scalar multiplication. If we look at the properties of matrix multiplication, there are a lot of similarities with real numbers, but there are some things that you got to be careful of. First off, matrix multiplication is not commutative. That means if you take A times B, it's not necessarily equal to B times A. Now you can find some matrices where this does work out, but in general this is not true. Just like subtraction of real numbers. If we were to take 3 minus 4, this is not the same thing as 4 minus 3. So just like with real numbers, A minus B is not the same thing as B minus A. In general, although you can find numbers for which this works, same goes with matrix multiplication. In general, it's not commutative, although you may be able to find special cases where it does work out. Matrix multiplication is associative, and if you were asked, if you were trying to prove this, this is just tedious. You actually have to go through a very long-winded argument, with a lot of subscripts in here. But the gist is that multiplication does have the nice associative property. So if for some reason you need to shuffle parentheses around, you can do that. There's also, if we mix matrix multiplication and matrix addition together, we have two distributive properties, just like we did with scalar multiplication. That is, if we take a matrix times the sum of two matrices, we can distribute the matrix through A times C. Now it's important to remember that a multiplication is not commutative, so the order matters. If A was on the left, A must be on the left for each of these matrices. And we have the same version the other way around. So if we've got, say, two matrices added together times a third, we can distribute the third one through. So this gives us A times C plus B times C. And again, I want to point out C is on the right-hand side, so when we multiply this through, the C has to stay on the right of both of those separate terms. And finally, we've got the identity matrix. Now, the identity is a little bit funny because if we take the identity matrix, this is the matrix. If I take I2, this is the two-dimensional identity. This is a 2 by 2 matrix that has 1s on the diagonals and 0 everywhere else. When we're using Gauss-Jordan elimination to row reduce a matrix, remember we're trying to make it look as close to the identity as possible. So if we take the three-dimensional identity, this is 1s along the diagonal and 0s everywhere else. Now the identity has this nice multiplication property where if I take the m-dimensional identity and I multiply it by a matrix A, where the matrix multiplication makes sense, it doesn't change the matrix. It leaves it as is. And if I do the other order also, now A might have a different number of rows and columns, so this may be different dimensional. As long as the multiplication is defined, if we multiply these together, it leaves the matrix unchanged. So those are our last two properties for matrix multiplication, is the identities. And we do have a new operation in here called transpose. So this is given the symbol if A is your matrix, something that looks like an exponent of T, this is the transpose of A, and this is read as A transpose. Now transpose means you fix the diagonal and everything else flips around. So if I were to take the matrix 1, 2, 3, 4 and transpose it, now the 1 and the 4 stay, everything else switches, so the 2 and the 3 flip places. So you can think of the rows and the columns switching roles. So if I were to take this with a non-square matrix, say 1, 2, 3, 4, 5, 6, if I were to transpose this, the first column becomes the first row of my transpose. The second column becomes the second row. So that's the definition of transpose for a matrix. Now transpose has some nice algebraic properties also. The first one is that if you transpose and then transpose again, you just get back to where you started. And that should be fairly straightforward. If we were to keep the diagonal fixed and flip these around, we just flip them back and we're back to the original matrix again. Transposing works well with addition. If we transpose a sum, we may as well just transpose the first matrix and then transpose the second one and add them together. So transposing works nice with sums. Sums work well. They're friendly with other operations, and products aren't necessarily. Scalar multiplication works. Now C transpose doesn't necessarily make any sense. The C just comes right out of the transpose. So we can decide to transpose the matrix first and then scale, or we can scale and then transpose. And if you write out a matrix, you can convince yourself that this is true. However, matrix multiplication and transpose do not get along. When we multiply this, the order actually switches around. So we get B transpose times A transpose. So these are the basic properties of matrix operations: addition, scaling, matrix multiplication, and transpose. And we'll look at more of these in depth in the next section when we get into matrix inverse.